let's talk about t-distribution and confidence interval. In most cases, when you have a sample, you do not know the population standard deviation. Very special case would be, say that you have a machine that once you pick a location, it kind of puts some nail around it, and you know the variation of that machine, but you just don't know where the location was. In that case, maybe you can use the variance of the entire population, but other than that, usually if you try to get a sample, you don't have any idea of what will be the average of the entire population, nor what will be the variance of the entire population. Since standard deviation is square root of the variance, that means you also don't know the standard deviation of the population. I forgot to say, all right, so to reiterate what I said last time, so there was a person who looked at this problem of if you have a normally distributed data set, but you don't know what the mean value is, you don't know what the standard deviation is, you only get it from the sample. So you get 10 resistors, you take the sample, and what you do is you add up all the resistance and divide it by 10, and let's say you got 95. And then let's also assume that each resistance minus 95, square them, add them up, and then you divide it by what? You divide by 9, because you're doing the Bessel correction, right? That's one of the first homework. Try to use Python to actually figure out that indeed dividing by n-1 is better approximation of the population standard deviation than dividing by n. Okay, so that's what S means. Okay, so you have to be careful when you see the symbol mu and sigma. Mu is the symbol for population mean, and sigma is the symbol for population standard deviation. The very fact that I'm using alphabets rather than Greek letters, this means these are values obtained from the sample. And by convention, whenever you see this S, that means it's the Bessel corrected version. Okay? I just put some simple values for us to calculate easily. All right, so you have such a thing. Then this sample mean has more uncertainty than a regular normal distribution because we're guessing the standard deviation, right? You're using one of the information to guess the standard deviation. And the distribution that accounts for this more uncertainty is called the t-distribution. Okay. So let me explain this a little bit compared to the normal distribution. So if you have normal distribution, then we know that minus 1.96 sigma and plus 1.96 sigma, and this is not 6, this is sigma. Subtracted from mu and added from mu. So here in the middle it's a mu. This captures 95% of the data. Okay? So if you take the z-score, the normal distribution is made so that if you take the z-score, between negative 1.96 to positive 1.96, the area under the curve will be 0.95. On the other hand, if you have 10 resistors, say, you could easily guess that the more the sample size gets, as the sample size gets bigger and bigger, the variance will be closer to the true thing, so that at the end of the day, you do have somewhat a better, more narrower distribution, which will be more like this one. Okay? But when you only have 10, there's a lot of uncertainty, and there's a concept of degrees of freedom. So degrees of freedom. This is given as n minus 1, and this minus 1 is a penalty for using the standard deviation of the sample as a replacement for the actual standard deviation. Okay? So here's a table that you can see. I should have printed this out, but degrees of freedom for our case is what? If it's n minus 1, what's our degrees of freedom?
9.
9. So we go to the table 9, and if you look at the two-tail right here, 2.262. So it says, let me just write down what's on the table. So it says one tail, two tail, with degrees of freedom 9. If you look at degrees of freedom 9, there's one tail that says 0.025. Two tail 0.05. And this number is 2.262. So if you look at where these two meet, and let me try to explain what this means. It means that if you're looking at one tail, and this is a t-distribution, they look very similar, but t-distribution is just a wider normal distribution. Okay. Of course, their formulas are very different. This decays exponentially. This doesn't. This decays like 1 over some polynomial. Okay. But overall, they both look like bell shape. And if you go from 2.262, negative infinity to 2.262, and just look at the right tail only, the right tail will be 0.025. That will be the area here. Okay? Now, if it's two-tail, what does that mean? That means if you go from negative 2.262, because the T curve is still symmetric, okay? Then this is also 0.025, so that if you add these two, what would you get? This plus this would be?
0.
0.05. And therefore, what's in the middle? How much is this much?
0.95.
0.95. So this will be capturing 95% of the data. Notice that for the normal distribution is 1.96, but for the t-distribution it's 2.262. It became larger. Now, if the degrees of freedom were smaller, this number would be bigger, right? There's more uncertainty, and you can see that. You can see that these numbers, as it goes up, it becomes larger and larger, right? And especially for degrees of freedom 1, it's as big as 12.71. Very large, okay? Is that okay?
That's right.
Any questions? Okay, so now let's try to solve this question. So when we use the t distribution, we're going to use something called t statistic, or t-score rather than the z-score. And you do exactly like how you compute the z-score. Okay? It's just a way to normalize it so that the curve becomes like this one. Centered at 0, and then its size is somewhat changed by using this. Okay, so what we do is, see, first of all, because we're taking 10 resistors, the average will now be, so I don't know how to write this. Right. I'll just write it like this. So that will be the standard deviation of the average. Okay. And what is this one? This is 6 divided by square root of 10. What's that? Someone help me?
1.9.
1.9 what?
1.897.
897. Okay. All right, good. It's more like 1.90. Okay. So that's what we have as the variance of 10 resistors average. If you take average, they vary less, right? Their variance decreases by square. Their standard deviation decreases by square root of n. Right? Okay, and then you use this to now normalize. So if you have this x bar, that's my average that I just took, and subtract from it the hypothetical mu that we don't know, and divide it by 1.90. This will be our t-score. And what captures 95% of the data? If this t-score is between negative 2.62 to positive 2.62, it's going to capture 95% of the data. So we're almost done. So let me still write down df equals to 10 minus 1 equals 9, because you do this, 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 and this is what you used to solve. Okay, so let's see what happens when this is equals to 2.62. So x bar is, we have it as 95. So 95 minus mu over 1.90 equals to 2.62. Multiply this to the other side and you get 95 minus mu equals to 2.62 times 1.90. And you move this over here and move that over there, so you get 95 minus 2.62 times 1.960. So when mu is this value, it attains the maximum. And what happens if you had a minus in here? And this will be minus, this will be minus, this will be plus, right? So you see that the two extremes are 95 plus this times that. This is plus 2.62 times 1.90. And just to make sure that we know what we're doing, let's write this down in the original symbol. What was this one? This was x bar plus minus. What was this one? This is what we call T alpha over 2. This value here is what we're going to call T alpha over 2 times Sx divided by square root of n. And this formula basically says that if I know the critical value, critical t value for the 95%, if I use this, then 95% of the time, it will be the case that the average value of the entire lot would be within this range. Okay. All right. So let's add 291 and 90.709.
709.
709. Okay. 701. Okay. And we see that the average of the entire lot would be somewhere between here. Okay. For that much. Yes. You have a question?
What is the alpha over 2 subscript on T?
Right. T alpha over 2 subscript is, right, there's something called the alpha value, which is defined as 1 minus confidence level. And in our case, I said 95% confidence interval. So our confidence level will be 0.95, okay? So 1 minus 0.95, which is 0.05, okay? And then you've noticed that if we are talking about this symmetric t distribution, and for confidence intervals, we are looking for two-tailed. Confidence interval is always two-tailed. So you have this two-tailed here and there. And what was this value? It was half of this, because we were going to put half of it here and half of it there, right? So this alpha over 2 for us is 0.025. And when you look at the t distribution table, that's why we were looking at this value for one-sided. Okay, so we looked at the one tail as 0.025, right? Yeah. And the reason was by calculating this. Okay. Thank you. I almost forgot to say what it is. Okay. So from here we found out that T alpha over 2 is 2.262 from the T distribution. And then what else? Yeah, and then this is a confidence interval. Is this okay? All right. What if it's the same question, but instead of this, sigma equals to 6 was given? How would the problem change? I mean, how would the solution change if the sigma was given? Somehow the manufacturer gave you the standard deviation. They say, oh, our resistors are off by 5% or something. Our variance is something. And then you trust them and you use it. In that case, what's going to happen?
Less degrees of freedom.
No.
So would it divide by the square root of 10?
You would still divide by square root of 10. Square root of 10, this is simply from the fact that the value, this value is obtained from averaging 10 resistors, so this value varies less. It doesn't change that much. That's what this means. Okay. If sigma was given, the difference would be that you use the normal distribution instead of t distribution. Get that? So instead of that, we'll be using the table. So I said that if you look at the z-score table, then negative 1.96 plus 1.96 captures 95%, right? So this 2.62 would be replaced by 1.96 so that the confidence interval will be smaller. Okay? Is that okay? if the confidence interval is smaller, does that mean you know more or you know less? Are you more certain or are you less certain? You're more certain. If the confidence interval is bigger, that means you don't know where it is. You have less idea of what the actual average would be. If it's narrower, then you have a better idea. It should be here, not there, right? You have more information. Okay? So, if the standard deviation is known, then you'll be using the normal distribution and you would get smaller confidence interval because you know more. So you get the difference between a normal distribution and t-distribution. This is very important. You have to know when to use the normal distribution and when to use the t-distribution. T-distribution just penalizes for the fact that usually you don't know the population standard deviation. You have to use what you have. Okay? When the degrees of freedom is like 1,000, when degrees of freedom is 1,000, the T alpha over 2 for 95% confidence interval is 1.962. How's that? That's very close to the normal distribution, isn't it? Yeah. It's very close to the normal distribution. So, in other words, if the size is big, then you can just use the normal distribution and you don't have to worry about the t-distribution at all. So usually when you do surveys and polls, like political surveys, do you want to vote for Donald Trump or do you want to vote for Joe Biden or somebody like a third party or something? You call people up and then you gather information and that gets charted, right? Usually the surveys are 1,000 or more people. And for those cases, you don't use t-distribution because you don't need to. At that point, there's not much of a difference between normal distribution and t-distribution. Okay? And in fact, because it's hard to have a chart for all the t-values, the rule of the thumb is that if your n is bigger than 30, then you can just use normal distribution. It's not going to be that off. What's 30? It's still 2.04. So when degrees of freedom is 30, t alpha over 2 is 2.04, and there's like 0.08 difference between 1.96 and this number. So it's I mean, people consider that as not that much, and they just start using this. Of course, nowadays computation is cheap. It used to be the case that if it's over 30, you just use normal because a long time ago computation was not so cheap. So that's why they did it. Nowadays, people say just use t-distribution all the time if it's less than 1,000. Okay. Some basic facts. df is n-1. You definitely have to know that. Of course, these are given in the formula sheet, but if you don't know what it means, even if you see it in the formula sheet, it doesn't help you. So you really need to know what this means. Okay? And then alpha is 1 minus the confidence level. And then T alpha over 2 can be either obtained from the table, or you can also use a TI-84 if you have one. This inverse T of 1 minus alpha over 2 with the degrees of freedom supplied. Okay? So that's what you can get. And then this E, which is known as the margin of error, this is T alpha over 2 times S divided by square root of n. This is called the margin of error. Okay. Then the confidence interval is confidence interval, CI, not CL. CI is the population mean, mu, is between x bar plus E and x bar minus E. Now, I'll just use the strict inequality, but because these are continuous variables, it doesn't matter if you put an equal sign or not. But that's the confidence interval. And if you think about what we just said, that this is exactly what we did, right? We obtained these formulas by solving t equals to x bar minus mu over Sx divided by square root of n. That's what we did. But if you multiply this around, and then you get the t alpha over 2 times this, and then if you solve for mu, these are the formulas that you get. Okay? So that's how you find the confidence interval.